This video is going to show you how to apply the net force equation idea to solve problems. Recall that the net force equation just simply says that the net force is in the direction of the acceleration and proportional to the acceleration. In addition to seeing the net force equation applied, you're going to, when you finish this video, you should be able to use the suggested problem starting strategies, be able to build and use a net force equation to solve a problem, and be aware of the proper amount and kind of work to show when you're solving such problems. The problem solving strategies that I want to walk you through include the following. 1. Decide if the problem should be solved using motion concepts and tools, or forces concepts and tools, or both, that is, some combination. If it's a problem that can be solved simply with the motion concepts you know from the first few weeks of class, well then you know those problem starting strategies and you can go ahead and solve the problem. If it looks like it requires a forces approach, then we'll have you list the interactions with the object and draw a free body diagram and then build the net force equations. Let's see how that looks with a sample problem. Here's a sample problem. You need to move some heavy firewood logs 34 meters across a field of snow to a stack of logs. You have the logs in a 30-kilogram sled. The snow exerts 50 newtons of friction on your sled as you pull the sled into a headwind which exerts 10 newtons on the sled. You can pull the sled with 85 newton, and as you do, the string on the sled makes a 30-degree angle with the ground. What we're going to do with this scenario is determine things about forces and motion. For example, what are all the values of all the forces on the sled, and what are some of the motion concepts, like what's the sled's acceleration, maybe how long does it take to get across the field, that sort of thing. Well, if we want to figure out the forces on the sled, then we can look up here to decide, is this a force problem or a motion problem? Well, it seems as if you're going to answer questions about the forces on the sled, and you're given lots of things here, here, lots of things about the forces on the sled there, that is probably a forces problem. If we're going to answer some things about motion, it may also be that, but most certainly it's a forces problem. So that tells us that we're going to have to use some of the forces problem solving strategies. But not every problem will be like that, so don't just assume that it will. All right, here are the forces problem solving strategies. List the interactions with the object, in this case the sled. Draw the free body diagram and build the net force equations. Let's go ahead and have you list the interactions with the object. All right, the forces that I got, the interactions I got with the sled are the ground, the earth, the wind, and the string or the rope. And I'll use rope so that we don't get string confused with sled in our subscripts. Now the next problem starting strategy includes building a free body diagram. That's to help us inventory and visualize the forces on the object. Why don't you go ahead and do that and then check your work with the video. And you can pause it and then unpause it. All right, here's the free body diagram. We have the tension from the rope on the sled, the wind pushing backward on the sled, the friction force pushing backward on the sled, the normal force pushing up, and the earth pulling down. Now you'll notice those two are different lengths. That's because the sled isn't going to be accelerating vertically, and you have both the upward pull from the string and the upward push from the ground. That has to net out with the earth pulling downward, and that's why that force is bigger than that force. Those two together, or at least the upward part of that, plus that, should equal that, so it doesn't accelerate in the up and down direction. Now we're going to go ahead and build our net force equations. Okay, so for the net force equation, looks like this. We know that the net force is equal to the mass times the acceleration. Well, let's do that for both the x-axis here and the y-axis here. In other words, we'll have a net force x and net force y equation. Let's do the net force x equation first. All right, along the x-axis we have the tension rope on string, but only the x part of that pull. It's pulling somewhat horizontally and somewhat vertically. We only want to capture the horizontal part of that. And then we have the friction wind on sled acting backwards, and hence the negative sign. And also acting backwards, or in the negative direction, we have the friction ground on sled. There are no other x forces, so those forces net out to be related to the acceleration, at least the horizontal acceleration. Now we can build a net force equation for the y direction. Why don't you pause the video and try to do it yourself and then come back. Alright, so this net force equation looks like this. Tension rope on sled in the y direction, plus, that is in the same direction as that, the normal force ground on sled, minus the earth pulling down on the sled, and that's going to equal MAY, where this mass is the mass of the sled. Okay, so the first thing we want to do if we want to make use of these equations is to break down the rope on sled vector into its vertical and its horizontal components. And I know you know how to do that, so you can do that and then double check your work here. Tension rope on sled in the x direction is equal to 73 newtons. Tension rope on sled in the y direction is 42.5 newtons. The other thing you can do is figure out the weight of the sled. But I'll do that here for you too. So let's answer the question. What is the normal force? Question. What is the normal force ground on sled? How much force is that? Alright, well we can use our net force equation over here. And I'll show you how that looks. This is 42.5 plus normal force ground on sled. That's what we want to know. Now the earth on the sled, we can do an algebraic substitution. That should be equal to g times the mass, gravitational field constant times the mass. Here we've got 50 kilograms for the mass of the sled and the logs, and the acceleration in the vertical direction is just 0. It's not accelerating up or down. Let's do one more substitution. 42.5 plus normal force ground on sled minus, this will be 9.8 times 50 equals 50 times 0. Now you'll notice there's only one unknown in that equation. That's the normal force ground on sled. And so you can just solve for that. And when you do that, you should get 447 newtons. Alright, let's say we want to know what the acceleration of the sled is along the ground. Well, again, we can use our net force equation. That might seem like a motion problem, but in fact we're not really given much about the motion. We're given maybe its distance and probably its starting velocity is 0, but that's about it. But we do have lots of information about the forces, and that allows us to calculate things about the acceleration, about the motion. So let's go ahead and do that. There's the value we want, the x acceleration. And so this is 73 newtons. This was 10 newtons. This is 50 newtons. And all of those come from the values up here, plus the tension, the horizontal component of the tension. This is again 50 kilograms. And there's our a sub x, our value we're looking for. And you can go ahead and calculate that. Comes out to 0.27 meters per second squared, at least rounded. Now, you could take it a step further. You might want to know what is the amount of time it takes to get across the field, or something like that. And at that point, you really have a motion problem. So, for example, you could write out a delta x equation equals VAX. Well, it's only one-dimensional motion, so we don't even need to do that. Delta x equals VA t plus 1/2 AT squared. Sled starts here at A, ends here at B. So then delta x, 34 meters, that's from right there, equals 0t plus 1/2. times the acceleration, which we just found out, 0.27, times time squared. And that comes out to about a little bit less than 16 seconds. So you can see we can solve problems both with motion and forces now. And with a forces approach, we can draw our inventory our forces, draw a free body diagram, build our net force equations both in the x and the y, and then use those to try to solve the problem.